In the last lecture, we learned about the double integrals with a rectangular domain, where we have an easy to deal with ABCD rectangle as the base of the integration. Today, the integration domains will no longer be a rectangle. They could be circles, triangles, ellipses, or other geometric shapes. They could also be bounded by different kinds of curves like polynomials, parabolas, exponentials, and so on. We call these non-rectangular forms of integration domains R as general forms. So it's going to be about this general domain today. And by the way, we need the Fubini's theorem number 2 in order to solve them. Okay, let's get started now. First of all, let's write down a few important points right here. Number 1, it's going to be about the non-rectangular integration domains today. So it's going to be about non-rectangular integration domain R. And number 2, we need the Fubini's theorem number 2 in order to solve them. Fubini's theorem number 2 is needed today. For number 1, we have covered that in the last lecture. Number 3, the order of the integration cannot be swapped freely. When I talk about the order of the integration, I'm talking about dx dy or dy dx. So this time around, dx dy or dy dx cannot be swapped freely. Be swapped freely. What this means is that you can't just pick any of them and works the same way. You need to pick the right one. You need to pick the more suitable one in order to solve your problem more efficiently. So this time around, you need to think wisely when it comes to this order. Cannot be swapped freely this time. And since they cannot be swapped freely, we need to pick them. And we need to pick them based on the shape of the integration domain R. Alright, this is how we pick them. Pick either dx dy or dy dx based on the shape of the integration domain R. Based on shape of R. Okay, according to the Fubini's theorem number 2, the general domain that we are going to deal with today have two distinct types. We have type 1 and type 2 right here. So let's take a look at the type 1 and its properties right here. An integration domain is considered to be type 1 when they have these two properties. So let's take a look at number 1 right here. They are all going to be related to the boundaries. So number 1 is going to be about the left and the right boundaries. So number 1, left and right boundaries are supposed to be straight lines. So here comes the keywords, are straight lines. So we expect the left and the right boundaries to be flat. Straight lines, and let's underline that. Very important. Now let's take a look at the properties number 2. Now that we have talked about the left and the right, of course we have to talk about the lower and the upper boundaries. So lower and upper boundaries. Okay, this time around are supposed to be curves. Okay, now you see the main difference between left and right and the lower and the upper, straight lines and curves. What does that look like? So let's take a look at an example of that on the figure on the right hand side, and we are going to draw it right here. So around here, okay, y-axis and x-axis right here. So let's start with the left and the right boundaries. So left one supposed to be straight lines, maybe something like this. Go straight down all the way through. And the right one, maybe something like this. Okay, I'm done with the left and the right. Now let's move to the lower and the upper boundaries. So lower one supposed to be curves, all right? Maybe something like this. Has to be curvy, right? Okay. And for the upper boundary, something like this. Okay, this is good enough. Now that we have these four boundaries, we can trap the region between them. And I'm going to start with the straight boundaries on the left and the right. I'm going to use blue color for that. Straight one on the left and straight one on the right. Now for the upper and the lower, which are curves, I'm going to use red for that. Lower curve and the upper curve. And there you go, we have this region, and it's going to be the general form of the integration domain R. Okay, so what we are looking at is the integration domain, and we want to perform the double integration over this region. Okay, now let's take a look at the range of the variables inside this region. Let's start with the x variable. As you can see, for the x variable, they are supposed to be in between these two straight lines, right? X has to be in between these two lines. And since these two lines are straight lines, I can use a constant to represent them. I can say that, hey, the left one happens at x equal to maybe a, and the right one happens at x equal to b, which means that I can use this equation x equal to a to represent the left boundary, and x equal to b to represent the right one, the right boundary. And as you can see, that's why we have this range inside the definition of this domain set right here. Integration domain is going to be this. X has to be in between a and b. So what you see a right here, you can make a note. A right here is the left boundary, and b right here is the right boundary. Okay, now we are done with the x variable. For the range, now let's take a look at the y variable. And as you can see, y can range between these two curves, the lower one and the upper one. When you see two curves like these two, they can be expressed by using functions. So I can say that the lower curve like this one, I can call it to be g1 of x. Okay? And the upper one is going to be a different function. So I'm going to use g2 of x for the upper curve. And as you can see, y has to be in between them. And that's why you have this range inside the definition. Y has to be in between these two functions, right? g1x and g2x. Okay, g1x is going to be the lower, all right, boundary, and g2x is going to be the upper boundary. Okay, this one is upper. Okay then, now let's move to type 2. Okay, that what we talked about earlier is the example for type 1. Now we move to type 2. So for type 2, it's going to be similar to type 1, except that the properties are going to be the other way around. So let's take a look here. It's going to be about the boundaries again. Number 1, this time around, it's the upper and the lower. So lower and upper boundaries are supposed to be straight lines instead. Are supposed to be straight line. Okay. This time it's the lower and the upper that have to be flat. Now for the second property, as you might have expected, it's going to be the left and the right boundaries, okay, are curves. All right, so we swap the properties between these two types. All right, curves this time. Now let's take a look at the an example of that right here. Okay, y-axis and x-axis right here. All right, so the lower and the upper boundaries are supposed to be straight lines, so let's build that. Lower one, straight line all the way through, flat. Upper one, like this. Okay, and let me add this y-axis right here. Okay, left and right boundaries are supposed to be curves, so could be something like this. And for the right one, could be something like this. And just like I did before, let's start with the flat boundary. Upper one, it's going to be blue, and lower one blue again. And for the curves on the right and the left, it's going to be this on the right and this one on the left. And as you can see, this is the region between these four boundaries. And once again, this is type 2. General domain R. Okay, now we are going to take a look at the range of the variables again. Let's start with the y first. So, as you can see, y has to be in between these two straight lines, right? The upper one and the lower one. And since they are straight lines, I can use constants to represent them. I can say that the lower one happens at y equal to c, and the upper one happens at y equal to d maybe, all right? So I can say that this one can use this equation y equal to c, and the upper one can use this equation y equal to d to represent. Okay, and that's why we have this. Y has to be in between c and d right here in the definition of this domain set of type 2. Okay, so make a note again that c right here is the lower boundary this time, and d right here is the upper. Okay, now let's move to the x variable. As you can see, x has to be in between these two curves, red curves, right? And just like before, we are going to use a function to represent each line. And this time, maybe we can use this h1 to represent this left curve, and h2 to represent the right curve. When you have a curve like this that goes upward and downward, you know that this is not a function of x, right? You cannot use h1 of x like this for a curve like this. So instead, you can use a function of y instead. All right? Instead of x, we can use this as a function of y. And same for this h2 as a function of y. Okay, and the reason for that is because this kind of curves, they go upward and downward. And that's why you can see that x variable has to be in between these two functions inside this definition of domain set. X has to be in between this h1y, and that's going to be the left boundary. Okay, and h2y right here is the right boundary. Okay, now I want you to take a note on this one, because this is quite different between these two types. For type 1, y has to be in between two functions of x. As you can see here, we are looking at two functions of x. So make a note. These are functions of x, and we are talking about y variable right here. For type 2, it's going to be x variable between two functions of y. All right. So make sure that you are aware of this obvious difference between them. Functions of y. Okay, now that we have seen the definitions of these two types, the properties, the example, now we can move forward to try to solve them. And the first step when it comes to solving these double integrals with a general domain is to determine the type, whether it's type 1 or type 2. And as you will see in the next slides, each type needs to be solved a little bit differently. Okay, let's move to this slide right here. First of all, I am going to give you the rule of thumb when it comes to solving the double integrals with the general domain right here. So we have this rule of thumb, okay, which by the way is the rule that you always need to follow. Okay, so what does this rule say? It says that you always integrate between two curves first. So let's write that down. Always integrate between two curves, or you can call them functions. Either ones are fine. Functions first. Okay, by the way, this is related to Fubini's number 2, theorem number 2. Okay, so this is one rule that you need to keep in mind and apply it to both types of the general domain, whether it's type 1 or type 2. Okay, so we are supposed to integrate between two curves. Well, how do we know if it's going to be between lower and the upper curves or between left and the right curves, whether it's type 1 or type 2? In order to determine that, we always need to see the shape of the integration domain R. Okay, so let's apply this rule to some examples right here. So let's assume that we have this multi-variable function f of xy. Okay, f of xy right here, and we want to perform the double integration on this function. So we are going to integrate this function twice. Okay, and it's going to be over an integration domain R. This time around, this R is going to be general domain. So make a note that this one is going to be general. And since this is general, we need to pick the x dy and dy dx wisely. We can't just pick any one of them. So in order to pick that, we need to see the shape of this integration domain R. So let's assume that the shape is shown right here in the figures down here. So this is the shape of R. And let's take a look at the left one first. So when you see something like this, you see right away that the left and the right boundaries are straight lines, are constants. So we have this constant. I'm going to use blue again for that. Alright, for the left and the right boundaries. Now, as for the lower and the upper boundaries, you can see right away they are curves. Okay, this lower curve and the upper curve. So when you see something like this, from the definition, you know right away this is type 1. Okay, so no problem with this one. Now let's take a look at the next one on the right hand side. It doesn't seem to have a straight line in this region, but we can see the lower boundary and the upper boundary. So let's take a look at them first. So here we have this lower boundary as a curve and the upper boundary. And to be honest, actually this region has the left and the right boundary, but it turns out to be a dot, just 1 point on the left hand side and another one on the right hand side. It's a constant, so you can make a note that constant value, but it's just 1 point. Okay, constant. So with this kind of value, you can assign it to be A and B, just like before, A and B. So as you can see here, they are quite similar in terms of the characteristics. So with this one on the right hand side, you can safely call it as type 1. Okay, constants on both left and right, curves on the upper and the lower. So type 1. Okay, now back to the rule of thumb. We always need to integrate between two curves first. So it's about this. We are going to integrate between this curve, lower curve, and the upper curve. Since this is the same type, we are going to do the same thing. Integrate between this curve, lower curve, and the upper curve. Now let's take a look at the lower curve. The lower curve is represented by this function g1 of x, and we are going to integrate between this g1 of x to the upper curve, which is g2 of x. So following this between two curves. So let's complete this double integrals in the upper part of this slide. So I'm going to erase this r right here and this general form right here, and instead of that I'm going to put this integration between two curves. So it's going to be between g1 of x, right, and g2 of x. And as you can see here, between this g1 of x and g2 of x is the range for the y variable, right? Y is trapped between these two functions, ranging from g1x and g2x. So we are talking about this y variable. Well, I can just put y right here. between these two curves. So what you see right here, g1x, we actually have this y equal to g1x and y equal to g2x, just like right here and right here. And it's going to be the same thing for the one on the right hand side between g1x and g2x. And we are talking about the y variable, and which means that we are supposed to integrate with respect to y first. So for type 1, we are going to integrate with respect to y first. And now that we see the first integration, I'm going to make a box around that. Okay, that is the first integration, and since this is too close, I'm going to move this a little bit further away. Alright, now let's make a note right here. For this type 1, by the way, this is type 1, we are going to integrate with respect to y first. Okay, integrate with respect to y first. Okay then, now let's take a look at this integrate with respect to y. When you integrate a function with respect to a variable, it can be considered as sweeping on that variable. So, and that's why you see this sweep y variable first right here, up here. What does it mean by sweeping? It means this: when you integrate over this region in y direction, it's going to create this sweeping pattern from the lower curve to the upper curve. It's going to create this kind of sweeping. Okay? Same thing here. Even though this one is small, it's going to sweep from the lower curve to the upper curve. Alright, this is like the sweeping characteristic or pattern. Okay, so that's what happens right here. Sweep y variable first. And since this kind of sweeping is going vertically, you can call this sweep vertically first. Okay, now that we are done with the first integration, we can move to the second integration. Of course, we have done the d with respect to y. This time around, it's going to be with respect to x. And this means that for type 1, it's going to be dy dx. You need to pick this order. You don't do dx dy. Alright? Now for dx, it's going to be this second integration, and we are talking about the range here. And we can see that range for x is between a and b, constants. Same thing here. So let's complete this. This is supposed to be between x equal to a constant and x equal to b constant. So during the second integration, what's going to happen? It's going to replicate this kind of sweeping over and over again until it covers the whole region. So it's going to do this. Replicate this kind of sweeping before from the lower curve to the upper curve, and then do again, right? Again. So give me some time, I need to concentrate on this so you know what I mean, right? Same pattern, sweeping vertically between two curves over and over again. As you can see here, we have like a big space between each pattern, but in fact it's going to cover very closely, so all the way through. Okay, that's the last one. Cover the whole region, same pattern. I'm going to do the same here. Give me some time. Sweeping vertically between two curves, lower and the upper. Okay, so you can make a note right here that we sweep vertically first. Okay, for this type 1. And now we know that for type 1, we go for dy and dx. Now let's move to type 2. For type 2, once again, I am going to put down the rule of thumb right here. Always integrate between two curves or functions first. Okay, now keep this in mind, and we are going to apply this again. This time around, we are going to do the same thing. We are going to perform the double integration on this multivariable function f of xy. Okay, and we are going to do this twice. And once again, we are going to do this over an integration domain R, which is a general domain. Okay, general. And we need to determine the type of this general domain first. So let's assume that this is the shape of the general domain this time. Okay, shape is this. Now let's take a look at what we have right here. Let's start on the one on the left hand side. Looking at this, we know right away that for the lower and the upper boundaries, we have this constant, straight line. Okay, constant at y equal to d, and lower one is at y equal to c. And for the left and the right boundaries, we have these two curves. Okay, this one on the left hand side and this one on the right hand side. The one on the left hand side is defined by this function of y, h1, and the one on the right hand side is this h2 as a function of y. Okay, you see this right away. You know from the definition that we learned earlier, this is definitely type 2. Okay, so you are confident right now that this is definitely type 2. What about this one on the right hand side? Okay, so alright, we have this constant value at the upper boundaries right here at y equal to d, and then lower part not so much. Alright, we have this just a point, but it turns out to be a constant. Alright, so even though it's just 1 point, it's a constant at y equal to c, and this one y equal to d. Okay, same thing here. Let me add this right here. And for the left and the right boundaries, we have this curve right here on the left. Okay, and on the right hand side we have this curve, and once again the one on the left hand side is defined by this function of y, h1, and on the right hand side this is h2 as a function of y. Alright, now we know that from this characteristic, this is definitely type 2. Okay, so what do we do now? We are going to stick with this rule of thumb again. We always integrate between two curves first. So we are going to do that. We are going to integrate between the two curves. This time it's between left and the right curve. Alright, left and the right curve. And as you can see here, between left and the right curve, it's going to be between this h1y and h2y. So let's put that in the integration sign. I'm going to erase this. We are going to integrate between two curves first. So first one from h1y to h2 of y. And as you can see, between h1y and h2 of y, this is the range for the x variable. We are talking about the boundaries for the x direction. So we have this x equal to h1y and x equal to h2y. Same thing here. Between these two curves is the x variable. And this means that the first integration has to be with respect to x, dx. Okay, so there you go. We have this first integration, and let's put a box around that. This first integration is going to be with respect to x. Okay, now let's make a note right here. Integrate with respect to x first for this type 2. Okay, now once again I need to move this. Okay, let me fix this one. Okay, this line right here, and then the second integration sign right there. Now, when you perform the integration with respect to a certain variable, it can be considered as you sweep through that variable. Since in this type 2 we integrate with respect to x first, it can be considered as you sweep through the x variable first in this type. And that's why you see this statement at the top, sweep through the x variable first. And this is going to show up as the sweeping pattern or characteristic in the integration domain down below. So let's take a look at this figure here. We are going to sweep the x variable first. How is that going to show up? It's going to be like this. Sweep from the left function, left curve, to the right curve. So sweep the x variable. It's going to show up as this arrow. Okay? Same thing here. Sweep from the left curve. Let me highlight that. Okay? Sweep from this to the right hand curve. It's going to create this arrow from left to right. So you can make a note right here that this one is the left. You sweep from left to right. Okay, now that we are done with the first integration, we can proceed to the second integration. We have done the integration with respect to x already, right? Now this time around, it's going to be with respect to y. And this means that when it comes to type 2, it's obvious that we have to choose this order of integration, dx and dy. Okay, now we need to integrate with respect to y, and as you can see here, the range for y variable starts from y equal to c and ends at y equal to d. Same thing here, start at y equal to c and ends at y equal to d. So we are going to have this y equal to c for the starting point and y equal to d as the endpoint. And this integration is going to replicate the sweeping pattern that we had before over and over again vertically until we cover the whole region. And it's going to do this. Start at y equal to c, we move a little bit further, and this arrow is going to get copied and sweep again between two curves and again. Alright. Never mind the big space between each arrow here. This is just an example. This is supposed to cover the whole region. It's supposed to be very close to each other. Alright, all the way through. And the last one, at y equal to d. Sweeping from left to right. Same thing here, left to right, left to right. Okay, going vertically until we cover the whole region. Okay, now last one, and here you can make a note down here that we sweep horizontally first here. So this represents the shape of the arrow that we have in this type 2, horizontally first in this type 2. Okay, now that we have seen type 1 and type 2, let's move to this next slide right here. In this slide, we have the Fubini's theorem number 2, and it's going to be the summary of what we have learned so far today. So theorem number 2 is going to be about the two types of the integration domains. And at this point, we know that we have two types. So let's start with type 1. It's going to be right here. Type 1 and type 2 down here. So let's spend a few minutes to understand the details of this theorem. So let's take a look at the type 1 first. Okay, we know in type 1, x variable has to be trapped between two constants, between two straight lines, right? So that's why we have this inequality right here. X has to be in between two values of a and b. So let's put a note right here that a is the left boundary, and b is the right one. Okay? And since we know that they are constants, they are straight lines, let's make a note that this is constant boundary, and this one is also a constant boundary. Now, as for y variable, y has to be trapped between two curves. And as you can see here, we have this inequality. Y has to be in between two curves or two functions. So g1x right here is the lower boundary. Lower function, alright, so lower boundary. And g2x right here is the upper one. And as you know, we have these two functions. They represent the curves in the space. So let's make a note right here that they are supposed to be curves. Okay, g1x is a curve, a function, and same with g2x. also a curve. Okay, that is the requirement for this type 1. Now for type 1, we are going to use this formula right here. Okay, double integrals. Okay, and as you know, when it comes to the type 1, we are supposed to integrate between the two curves first, because that is the one rule that we need to keep in mind. So let's write it down here. Integrate between two curves first. Okay, so let's change this to just a number. All right. So between two curves, we are talking about this g1x and g2x. We are supposed to integrate between them first, and g1x and g2x is the range for the y variable. And that's why we are supposed to integrate with respect to y first, right here, and then x later. And that's how we know that type 1 is going to be this order of integration, dy first, and then dx. Okay? So let's make a box around this. Type 1, it's going to be dy dx, always. Okay, when it comes to this integration, let's make a note right here. In this case, it's going to be integration with respect to y first. Integration with respect to y first. Right, which means that we are going to sweep the y variable first. So this also means that we are going to sweep y variable first. And when you sweep y variable, you go in the up and down direction, right? So this is going to be sweeping vertically first. Vertically. Okay. From lower curve to upper curve. From lower to upper. Okay, that's why we have this g1x right here and g2x right there. Okay, that's for type 1. Now let's take a look at the detail of the type 2. For type 2, the y variable has to be in between two constants, and that's why you see this inequality right here. Y between two constants, and y is when we talk about y, it's about the lower and the upper boundaries. So here we know that this c is the lower boundary, lower, and d right here is the upper. And since we know they are constants, let's make a note for that. Constant lower boundary and the constant upper boundary. Now for x variable, x has to be trapped between two curves this time, and that's why we have this right here. X are trapped between two functions, h1y and h2y. So h1y right here, it has to be left boundary. Okay, left right here, and this one is the right. And since we use functions for them, they represent curves, right? So make a note for that. This is supposed to be, right, curve, left boundary, and also curve on the right boundary. Now for type 2, we are going to use this formula. It's going to be similar to the one in type 1. It's about the double integrals again, but the only difference is the order of the integration. Alright, now once again we have this one rule to keep in mind. Integrate between two curves first. Integrate between two curves first. Alright, same one rule. So two curves, talking about two functions, and it's going to be this h1y and h2y. So we are going to integrate between them first, and when it comes to these two functions, it's about the x variable. And that's why we need to integrate with respect to x first and then y later. And that's how we know that for type 2, it's going to be this order, dx and dy. Okay. Now let's go into the details of this integration. So integrate between two curves first. In this case, it's going to be the integration with respect to x variable first. Integrate with respect to x first. Alright, So which means that we are going to sweep the x variable first. Sweep x first, and when you sweep x, you sweep in the horizontal direction. So it's going to be horizontally. Sweep horizontally from left to right. Okay, and we are going to have this h1y right here, the left curve, and h2y for the right curve. Now we have one questions about these four functions that we have right here. g1x, okay, g1x right here, g2x, h1y, and h2y. The question is, can we assign a constant to them? I know that I have told you all the way from the start that they have to be curves, but can they be straight lines? Can we assign a constant? Yes, we can. A function can be a constant, right? Same with the curve. Curve doesn't have to be curvy. Curve can be a straight line too. So we can make a note right here that g1x, this is quite important. Otherwise you might think that these four functions have to be curvy all the time. Right? g1x, g2x, h1y, and h2y. They don't have to be curvy all the time. They can be straight lines too. Can be constants. Can be constant. Alright, so this is the keyword. In other words, they can be straight lines too. Can be, okay, straight line too. Okay, keep this in mind. Okay, now that we understand this theorem number 2 for the Fubinis, we can proceed to apply this to some examples in the next slides. So let's start with this example number 3 right here. So let's take a look at the information that we have. In this example, we are supposed to solve this double integral, this one right here. Okay, and when you see this, okay, so we see this multi-variable function right here. So right away we know that this is f of x and y equal to x plus 2y. Alright, and we are supposed to perform this double integration over an integration domain D. Well, what about we change this to R? It's the same thing, but we have used R so far, right? So let's change it to R. So I'm going to change this to R, integration domain. Right? And let's find out whether this integration domain is rectangular or not. So this domain D or R is going to be bounded by parabolas. Okay, so the keyword is right here. Definitely non-rectangular. So make a note right here that this definitely is non-rectangular, which means that we are looking at the general form of the integration domain. So we are looking at general form, and which means that we are supposed to apply the theorem number 2. So this is about Fubini's theorem number 2. Theorem number 2 is needed here. Okay, let's take a look at these two parabolas that we have. The first one is y equal to 2x squared. Alright. Now, next one is the y equal to 1 plus x squared. And now we are supposed to perform the integration over this region trapped between them. Now, the question is, how do we proceed with this information? The first thing that we are supposed to do, oh, by the way, this is wrong. This is, I am not supposed to include d in there, x plus 2y. Because right now we have this dA, and we don't know whether it's dx dy or dy dx. And since this is general form, the order of the integration matters, so we need to pick the right one. And in order to pick the right one, we need to see the shape of this integration domain. Alright, number one that you should do right here, determine the type, alright, whether it's 1 or 2, by plotting graphs. Okay, and it's we are lucky that they provide the graph right here on the left hand side. So let's take a look at this graph and let's associate this with the information we have in the example. Alright, so we are going to find out about this type of this example. Alright, so let's start with this curve number 1, y equal to 2x squared. So we have this y equal to 2x squared, and let's draw this in the graph. So this one, it's going to be a parabola, but with this 2 right here, it's going to be a steeper version of a parabola, and it's going to be this line. Going to be this one, right? I'm going to highlight this again. Steep parabola. Okay, this is bad. Let me fix this. I need to make it steady. All right. Okay, give me some time. Right. Okay, going down right here and up. So what you see right here, this curve, let me highlight it. Okay, this is the first parabola that we have, and it's going to be this y equal to 2x squared. Alright, that is the first curve. Now let's take a look at the second curve that we have, second parabola, and that's going to be y equal to 1 plus x squared. Alright, so this one is going to be a parabola again, x squared, but this time around it's going to be shifted up 1 unit. Okay, and that's how we get this second parabola right here. I'm going to use blue this time for the second curve. Okay, so it's going to be a regular parabola shifted up 1 unit, and it's going to be this curve. So we are talking about this intersection with the y-axis 1 right here. Now that we have seen the two curves, we start to see the region trapped between them. And as you can see, the region is this. Okay, and it's going to be this integration domain that we are supposed to perform the double integrals over. So this is the one that we are supposed to work on. Now, the next thing we are supposed to do is to determine the type. So looking at this curve, this region, do you see two curves from the left and the right, or two curves from the lower and the upper? To me, I see one right here at the lower and another one at the upper, right? Okay, so to me, this is a type 1. Okay, so I see one at the lower portion of this region, lower, and this one is the upper. Now with this kind of form, I know right away this is type 1. So I'm going to make a note right here. This is going to be type 1. Alright, and type 1, I know it's going to be dy dx. Okay, in type 1, we are going to integrate with respect to y first. It means that we are going to sweep the y variable first. So it's going to be this arrow, starting with very close to the starting point. It's going to be something like this, and going up, I hope you see this arrow. Okay, and that is the first step. So at this point, we know right away it's going to be this dy dx, because the shape that we have right here, the region that we have, looks to be type 1 due to type 1. Alright, that is a good starting point. So let's use this information to solve the double integration. Oh, by the way, before that, now that we know the lower curve and the upper curve, why don't we assign them to functions? So the lower curve right here, I am going to assign this lower curve to be g1 of x, and the upper curve right here is going to be g2 of x. So this is going to be g1 of x, and this one is going to be well, what about this? This looks better. Okay, equal to g1 of x, and this is going to be equal to g2 of x, and this is the lower boundary, and this is the upper one. Alright, now let's proceed with the double integration. So here we have double integration. Alright, so something like this. I need to save some space, so I need to think about how I manage the the fonts right here. So here we have this x plus 2y. And at this point we know it's going to be dy dx. Okay. And now I need to complete this r right here. Instead of leaving as an unknown, I am supposed to add information to that. So first of all, I need to integrate between two curves. So it's going to be this between two curves. First one is this. From the lower curve, it's going to be y equal to, okay, y equal to 2x squared. To the upper curve, right, we worked on the lower and then go to the upper. It's going to be y equal to 1 plus x squared. Alright, and that is the first integration. Now, what about the range for the x variable for the second integration? We need to find out about that. About this information right here, starting point and the end point for x variable. Let's assume that we don't have this point available in the graph. Well, they gave this to us, but let's assume that we don't know. If we don't know about them, then we need to find out where this point is. And as you know, this point is going to be determined by the intersections between the two curves. And it's going to be this point, this intersection between two parabolas. So let's find out about these 2 points. Intersection about them. So let's write down y equal to 2x squared right here. 2x squared. And intersection means that they have to be equal to each other. So 2x squared has to be equal to the other curve, which is 1 plus x squared. So, by the way, this is intersection. Okay. Now, let's work on this equation. It's going to be x squared minus 1 equal to 0. So we have x minus 1 and x plus 1 equal to 0. And in the end, we know that this is true when x equal to 1 and minus 1. And there you go. We have the range for this x variable. For the intersection point, start at minus 1 and ends at 1. So we can complete this. X starts at minus 1, x equal to minus 1, and x equal to 1 right here. Okay, let me erase this. Okay, now that we have all these information, we can proceed with the integration. Alright, so I'm going to work on that right here. Okay, so this one, let's start with the inside integration first. So I'm going to work on this one. We need to integrate the inside integration with respect to y first. Integrate with respect to y first, and which means that we are going to treat x variable as constant, x as constant. Okay, so integrate this with respect to y, we get xy. First term, this one. Integrate x with respect to y, we get xy. Integrate this with respect to y, we get 2y squared over 2. 2 cancel with this 2 right here, it's going to be y squared. Okay, so plus y squared. And since this is a definite integration, we are supposed to evaluate this term at two values of y, which is 2x squared right here, and 1 plus x squared right here. So need to evaluate this at y equal to 2x squared, the lower curve, and y equal to 1 plus x squared, the upper curve. And don't forget that we still have the other integration sign that we have to include, x equal to minus 1 and x equal to 1 dx. Okay, now we need to put all these terms in. Okay, so integration sign still here, x equal to 1 and x equal to, x equal to minus 1. Right here is supposed to be x equal to minus 1. X equal to minus 1 to x equal to 1. Okay, so inside this is going to go in to y. So we have this x times 1
plus x squared. And this 1 plus x squared is going to go into this y right here because this is equal to y, right? So it's going to be plus 1 plus x squared. Okay? Now, minus the other terms is going to go in here. Y equal to 2x squared. So this is going to go in here, and it becomes x times 2x squared. X times 2x squared. Plus, this terms goes in right here. 2x squared and square again. 2x squared and square again. Okay, this is quite long. Okay, so in the end, we are supposed to integrate all these terms with respect to x. So let's clean up these terms and make it look nicer. So I'm going to work on the side. So this is going to be x plus x cubed, right? Plus, so we are supposed to square these terms right here. So it's supposed to be front plus 2 front back 2x squared plus back squared. That is going to be x to the 4th. Alright, now this one is going to be 2x cubed, and this one is going to be 4x to the 4th. And minus sign at the front right here is going to go to here and here. Okay, now I'm going to combine all these terms, and it's going to be 1 first, right here. 1, and we have x right here, plus x, and we have 2x squared, plus 2x squared. X cubed minus 2x cubed, it's going to be minus x cubed. X to the 4th minus 4x to the 4th, I have this minus 3x to the 4th. Okay, and we are supposed to integrate this, all these terms, with respect to x, starting from x equal to minus 1 and ends at x equal to 1. Okay, I know that we ran out of space, so I'm going to make a border like this. Okay, I'm sorry about this. Now, let's take a look at this. We are supposed to integrate this with respect to x. This is easy stuff, just one variable to work with. So this is going to be first term, integrate this with respect to x, I get x, right? Plus second term right here with respect to x, I get x squared over 2. This third term with respect to x, I get x cubed over 3. So we have this plus 2x cubed over 3. Now this one with respect to x, I get x to the 4th divided by 4. So I have this minus x to the 4th divided by 4. And I integrate this with respect to x, I get x to the 5th divided by 5. Minus 3x to the 5th divided by 5. And definite integration, of course, we have to evaluate these terms at two values of x. X equal to minus 1 and x equal to 1. Okay, now this is going to be equal to, well, let's put these terms in. X equal to 1 goes in here, here, and here, and all the way through. So I'm going to get 1 plus 1 over 2 plus 1 over 3 minus 1 over 4 minus 3 over 5. That's the first term. Now, I work on this one. X equal to minus 1 goes in here, 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 and here. So I get this minus sign at the front. Minus 1's goes in. We have this minus 1. Okay, minus 1. I think I run out of space, so what about I work over here? Continue over here. Minus 1 goes in. I have this minus 1. Minus 1 goes in, I have this plus over 1 over 2. Minus 1 goes in, I have this minus 2 over 3. Which means that I make a mistake right here. This is supposed to be 2 over 3. Okay? So, minus 1 goes into this x to the 4th. I get this minus 1 over 4. And last one, we get this plus 3 over 5. Okay, so we have some cancellation right here, 1 over 2 and 1 over 2, minus 1 over 4 and minus 1 over 4. And once you worked out all these terms, they are going to come out to be equal to 32 over 15. Okay, and that's the answer for this example. And this example is related to the double integrals with general domain with type 1. Okay, so make a note right here. This is double integral with general domain type 1. And as you know, we use this dy dx to solve this problem. Oh, by the way, about the sweeping pattern, when you perform the integration with respect to x, like what you did down here, integration with respect to x, when you did this, you are going to replicate the sweeping pattern, this green arrow, over and over again until you cover the whole region of the integration domain R. So starting at x equal to minus 1, you already have that sweeping pattern, the green small arrow. And once you perform the integration, your x value is going to increase. And as you can see here, when your x value increases, you are going to repeat this same pattern, starting from the lower curve, go straight up to the upper curve. Okay, x value increases, same pattern, lower curve, vertically up to the upper curve, lower to upper curve, lower to upper curve, or you can call them lower function to the upper function. And as you can see here, as we continue, this is going to cover the whole region of this integration domain R. And we are going to stop at x equal to 1 right there. So it's going to be the same vertical pattern, vertical arrow that cover this whole region of R in this example. And this example is for type 1 general domain. Okay, now that we have seen this sweeping pattern, let's take a look at the example number 4 in the next slide. In this example, let's take a look at the information that we have right here. It's going to be a repeat of example 1, which is wrong. So please change this to 3. So we are going to use the information we had from the last example, number 3. But this time around, we are going to perform the double integration over a different domain. So it's going to be a different R this time. I don't like this D, let's use R. But if sometimes you see D as the integration domain, that's okay too. So this new R is going to be bounded by this new parabola. So we have this first curve, x equal to minus y squared plus 4. Alright, minus y squared plus 4, and that's the first curve. And we have another line, that is y-axis. And as you can see here, the information that we have in this example is a little bit different than example number 3. Instead of two equations, two functions, we have y-axis in this example. Okay, now this is going to be a repeat of example number 3, which means that we are going to use the same multivariable function f of xy. So it's going to be this f of xy from the last example, and that's equal to x plus 2y. Alright, and now let's find out about this new integration domain R. First of all, let's determine whether this R is rectangular or not. And as you can see here, this R is bounded by a parabola. So definitely this is not rectangular. So you can make a note that this is non-rectangular domain. Non-rectangular. Which means that this is going to be the general form of the integration domain. General form. And it also means that we are going to need the Fubini's theorem number 2 in order to solve this. So theorem number 2 is needed again in order to solve this example. Alright, now let's get started with this example. So it's going to be a repeat of this example number 3. It's going to be this double integral all over again. Double integral. So let's use blue for that. Okay, double integral of the same multivariable function, x plus 2y, integrate with respect to this differential area over this new integration domain R, which I am going to use R right here for now. As you know, when it comes to the Fubini's theorem number 2, we need to find out about this dA, whether it's going to be dx dy or dy dx, because the order of the integration matters here. So the first question is, if this dA is going to be dx dy or dy dx. That is the question. Which one is the more suitable one in order to solve this example? In order to answer that, we need to know the type of this R right here. We need to know the type. And in order to know the type, we are supposed to see the shape of this region in the space. Okay? So quite a lot of things we have to do right here. So first of all, in order to answer this dy dx or dx dy, we need to determine the type. Determine type of this new integration domain R of R by plotting plotting graph. And in this example, we don't have the graph available like in the last example, so we are going to have to do that ourselves. So let's draw the graph on the left hand side right here. So this is the y-axis, okay, and let's have this x-axis right here. Now let's take a look at the curves and the lines that we have. First of all, we have this x equal to minus y squared plus 4. We have this line, this curve, x equal to minus y squared plus 4 as the first curve that we need to include in this graph. And we also have this y-axis. The question is, can we express this y-axis as an equation or a function? Well, the answer to that is yes. We can express this y-axis as x equal to 0. It means the same. Alright, so the other line or the curve that we have is this y-axis, x equal to 0. So you can make a note right here that this is the same as y-axis. Okay, two curves that we are supposed to draw in this graph. So let's start with the first one. So here we are looking at x equal to minus y squared, right? Looking at this minus y squared right here, we know right away this is a parabola on the side, x equal to y squared. But with this minus sign in the front, this is going to be a parabola on the side that points in the minus x direction. It's going to be negative x. And not just that, we have more. This 4 right here is going to shift your graph to the right 4 units. So it's going to be a parabola on the side points in the minus x direction shifted to the right 4 units. So let's draw that in this graph. So it's going to be 1, 2, 3, 4 units. Okay? And it's going to be a parabola on the side and points in the minus x direction, and it's going to be this. Let me use red for that. Oh, let me use blue for that. That's better. So it's going to be a parabola on the side, something like that. Okay? Not the best shape, but I try my best to keep it a parabola. So we have this 1, 2, 3, 4 right here. Okay, and x-axis and y-axis. There you go. That is the first curve. Let me highlight this. Okay, the first curve for this integration domain in this example. Now let's take a look at this next one. We did this, and let's take a look at this x equal to 0, which is y-axis. It's going to be this straight line. Okay. Alright. Now that we have these two curves, we can see the region that is trapped between them, and that is this region. Trapped between these two curves. Alright, and it's going to be this integration domain for this example, R. Okay, so we have this one on the right. Oh, I'm sorry. Alright, looking at these two curves and this region, the first thing that we need to do with this region is to determine the type. Now the question is, do you see two curves from the upper and the lower, or the left and the right? Okay, that's going to tell us the type, right? Between upper and lower, or left and the right. And as you can see here, for me, I see one on the left, which is this. red one, it's going to be the curve on the left. Even though it's straight, it's fine, it's a constant. And this one is going to be on the right. Okay, so to me, I see, I'm sorry, this is supposed to be right. So to me, I see this one as the right curve of this region, right border. Okay, so left and right, it means that this is going to be type 2. So to me, after seeing this region and the curve, I know it's type 2. Okay, and type 2, it's going to be dx dy, based on the formula in Fubini's theorem number 2. Okay, so before we proceed with the double integration, now that we know the left and the right curve or the lines, we can assign that to some functions right here. So this left is going to be h1 of y, all right, and the right here is going to be h2 of y. And that means that this is going to be, this one is going to be, this one is on the right. So this is going to be h2 of y, and for this one is going to be h1 of y. Okay, now let's complete the double integrations. Okay, so we have this double integration of this x plus 2y. Okay, let me make this a little bit bigger. Double integration of x plus 2y, and at this point we know that it's going to be dx dy because we see type 2 of the region. So it's going to be dx and dy. And with this same rule that we follow every time, we are going to integrate between two curves. Alright, so we are going to integrate from the left curve to the right curve like this. So from h1y to h2y. So from h1y, it's going to be this x equal to 0. This one right here. h1y to h2y, which is this. 2x equal to minus y squared plus 4. Alright? Okay, so let me clear this up. I need more space. What about I put this right here? Okay. What about this? I assign this to be h1 of y, h2 of y. And this one to be equal to h1 of y. So there you go. Now I need to move this a little bit further. Okay, now we have the boundaries for the x variable. No problems between two curves, right? Now here comes the range for the y variable. So we need to find the whole range of the y variable, and as you can see here, y starts at this point, the intersection between the parabola and the y-axis, and it's going to go up and ends right there, a constant. So we are supposed to find these 2 points. So let's find out about that. So we have these two curves, x equal to, this is about the intersection between the two lines or curve. Intersection. Alright. So the first one is x equal to minus y squared plus 4. And the second one is x equal to 0. So all we need to do is to solve this equation. And as you can see here, this is y squared minus 4 equal to 0. So we have y minus 2 and y plus 2 for the factorization, and in the end we know that y has to be equal to 2 or minus 2 to make this equation come true. So this is going to happen at two values of y at minus 2 right here, down here, and y at 2 up here, which means that the range for the y variable is going to be this, y equal to minus 2 down here and minus 2 and y equal to 2 up here. Okay, so there you go. We have the complete double integrals for this example. So let's continue to solve this. Once again, we are going to start with the inside integration. So start with this one. We are going to integrate this with respect to x. Integrate with respect to x. Okay, and we are going to treat y as constant first. Okay. Okay, let's do that over here. I need to save some space again. Okay, it's going to be equal to, all right? Now I need to integrate this x with respect to x. This is easy. It's going to be x squared over 2. Integrate this to y with respect to x. 2y is going to be treated as constant here, so I am going to get 2yx. 2y stays the same, and x show up at the end. And since this is a definite integral, I am supposed to evaluate this at two values of x equal to 0 and x equal to minus y squared plus 4. Alright. Oh, by the way, let's make a note right here that this is left curve. Okay, sweeping from the left to the right. Okay, now don't forget the other integration sign right here with respect to y, and y has to span from minus 2, y equal to minus 2 to y equal to 2. Okay, it's going to be messy again. So this value of x is going to go in minus y squared plus 4. Okay, it's going to go in there as x. So it's going to be this minus, okay, before that let me work on this outside. Okay, so it's going to be this minus y squared plus 4. Alright, and we have this square right here. It's going to get square divided by 2. Okay, this value goes in as x value plus x value minus y squared plus 4 goes in here. So it's going to be 2y times this x, which is equal to minus y squared plus 4. That is the first term. Okay, first value of x. Now we are supposed to minus the second value of x, and the second value is x equal to 0. X equal to 0 goes in here, is going to be 0, right? X equal to 0 goes in here, also 0, which means that the second term right here is 0. Well, that's easy. I like that. Okay, now let's work on this term right here. It's going to be front square. That's going to be y to the 4th. Alright, and we have this plus 2 front back minus 8y squared plus back square 16. And we still have this over 2 right here. Okay, plus this, okay, this is supposed to be minus 2y cubed and plus, okay, 8y. Okay, now we are going to get rid of this division by 2. I'm going to work on that right here. So it's going to be y to the 4th divided by 2 minus 4y squared. Alright, and 2 cancel with 16, we get 8 minus 2y cubed plus 8y. And we are supposed to integrate this with respect to y. At two values of y equal to minus 2, and between two values of y, and y equal to 2 right here. So equal to, first term with respect to y, I am going to get this y to the 5th divided by 10 minus, okay, integrate this with respect to y, we get y cubed over 3, right? So in the end we have this 4y cubed divided by 3. Integrate this with respect to y, this one is easy, plus 8y. Integrate this with respect to y, we are going to get y to the 4th divided by 4. And cancel with this 2, it's going to be minus y to the 4th divided by 2. Okay. Now, last one, integrate this with respect to y. It's going to be y squared over 2. 2 cancel with 8, we get 4 plus 4y squared. And we need to evaluate this at two values of y. Y equal to minus 2, alright, and y equal to 2 right here. And I'm going to work this out in a calculator. And if you got this correctly, it's going to come out to be equal to 17 1 over 15. And that is the answer for this example. And you can make a note that this is for the double integral. Double integral with general domain. General domain. Type 2. This time around is type 2. Okay, now we are back to this sweeping pattern. When you perform the integration with respect to y, like you did down here, right here, on the right hand side, when you did this, you are going to replicate this sweeping pattern that you already have again and again, from the left to the right as you increase your y value. Same horizontal arrow. Again and again from the left function or the left curve to the right curve until you cover the whole region of this integration domain.